Greetings, students. Mr. Harrison here from school. Here is a video for the electromagnetic waves and electromagnetic spectrum slideshow. Let's get into it. Electric and magnetic fields are the name of the game with electromagnetic waves, and that's why, in fact, that it's called electromagnetic waves. The synergy between these two things is what drives the wave. So what you have is you've got an electric charge, and an electric charge is always surrounded by an electric field. We know this about electricity. We also know that because of electromagnetic induction, that a moving electric charge produces a magnetic field. And then conversely, a moving magnetic field produces an electric field. So what happens is you've got an electric charge, which is represented by the portion of this wave that contributes to the blue part. And then you've got the magnetic field, which is the pink portion or the red portion. When you got an electric charge that's moving, it's vibrating, its electric field changes, creating a magnetic field. We know this already about electricity with electromagnetic induction. When you have a rotating or moving electric charge, it creates an electric field, and a rotating electric field creates a magnetic field. And then you've got a magnetic field that's also rotating, and a rotating magnetic field creates an electric field. So essentially what you've got is you've got an electric field that's rotating, creating a magnetic field. And that magnetic field is also rotating, which creates an electric field, which is also rotating. And that electric field that's rotating creates a magnetic field. And then the magnetic field is rotating, which creates an electric field. And that electric field is rotating, creating a magnetic field. And you're probably getting sick of me repeating myself, but that's exactly what the wave does. Both the electric field and the magnetic field, when they're rotating, fuel each other. There's a synergy there. There's a almost miraculous ability for these two things to like power each other. And it's this pattern of changing fields that produces an electromagnetic wave. It's very, very dependent on electric fields and magnetic fields simultaneously at the same time. As far as the wave properties of an electromagnetic wave, it behaves as a transverse wave, which is the opposite of a sound wave or compressional wave. It goes perpendicular to the direction the wave travels. So if this wave is traveling, if you can see my cursor, it's traveling this way, the energy oscillates up and down, which is perpendicular to the direction the wave is traveling. And each of these types of electromagnetic waves have specific wavelengths and frequencies. And if you remember from before, a wavelength is one completed wave. So starting at this point right here, it's the part where that part of the wave repeats itself. So we go all the way down until it's going up and crosses the rest point. So this entire portion right here is one wavelength. And the frequency is just how many of these crests and troughs there are, or how many compressions and rarefactions if it's a compression wave. And these wavelengths and frequencies are so unique that we actually identify them by their wavelengths and frequencies. Very interesting fact that kind of blew my mind the first time I heard it is that an electromagnetic wave travels at the speed of light. All of them do, because light is just part of the electromagnetic spectrum. So radio waves and microwaves and gamma rays and X-rays and ultraviolet rays, all of them travel at the same speed, which is the quote-unquote speed of light. It's really fast. 3 times 10 to the 8th meters per second is the speed of light. That's 3 with 8 zeros meters per second. To put that in perspective, it's roughly 300 million meters per every second. So every second, a light wave travels 300 million meters. It's very, very, very fast. And when an EM wave, by the way, EM is an abbreviation for electromagnetic. So if you see it written or spoken EM, that means electromagnetic. When an electromagnetic wave encounters an object, its field actually exerts a force on that object. So what I'm telling you is light actually exerts a small amount of force on an object. It's kind of crazy. The other crazy thing about waves in the electromagnetic spectrum is there's a super awesome nerdy term for it, that I believe was coined by Einstein, and it's called the wave-particle duality of light. Duality means two things at once, and the two things are waves and particles. What it basically means is that an electromagnetic wave behaves simultaneously as a particle, like an actual bit of matter, and as a wave at the same time. And the particle portion is called a photon. So it behaves, it's almost as if there's simultaneously like an actual physical thing there in terms of matter, and at the same time it behaves as a wave. It's the only thing we know that has this dual nature. So here is the entire electromagnetic spectrum. And basically what that says is just the entire range of electromagnetic frequencies. And as you can see over here, very low frequency on this end, moving this way, higher and higher and higher frequency. So the lowest frequency wave is radio wave. The highest frequency wave is gamma rays. And then there's a lot of things in between. And as you can see, this is like a zoomed in portion. This tiny little bit right here, that's all we can see. Most of the electromagnetic spectrum, we can't see. And if you didn't catch this, this is organized by the frequency of the wave or by the wavelength because they're related. And just to review, wavelength and frequency have an inversely proportionate relationship, which means as wavelength increases, frequency decreases. And as wavelength decreases, frequency increases. One cannot go up without the other one going down, and vice versa. So here's the whole spectrum. This tiny little snapshot here is visible light. And then the order is the Roy G. Biv thing that you probably heard in elementary school: red, orange, yellow, green, blue, violet, Roy G. Biv. That's an order from longest wavelength, lowest frequency is red, and shortest wavelength, highest frequency is violet. This is also an order for energy. Radio waves and red visible light is the lowest energy. Gamma rays and violet light are the highest energy. Whoops. All right. So the first section up here is radio waves. Let's talk about those. Radio waves are the electromagnetic waves at the longest wavelength. And if you could actually see the wave, you could, with the naked eye, see the wavelength. It's over 1 millimeter. That's the tiniest little notch on the meter stick. It's small, but it's visible to us. But most of these waves are invisible. So radio waves, if we could see radio waves at all, would be visible to the naked eye. We wouldn't need a microscope, but it's a moot point because we can't see them anyways. They are used in communications, radar, MRIs, obviously radios, and they're the longest wavelength, lowest energy wave on the spectrum. A little bit shorter wavelength, a little bit higher frequency, higher energy is microwaves. They're actually technically part of radio waves, but they're the higher frequency, shorter wavelength version of radio waves. They have a wavelength of less than 30 centimeters, but longer than 1 millimeter. And the cell phones and satellites we use microwaves. So your cell phone signal that comes from the satellite is in the microwave category. And then obviously microwave ovens use microwaves. Interestingly enough, the microwave ovens do not actually heat up the food. They just speed up the water molecules. So as the water molecules speed up, we know from the forms of energy unit that kinetic energy, the average kinetic energy in matter is the temperature. So as you speed up, add more kinetic energy to the water molecules, the food will quote unquote heat up as it raises in temperature, because temperature goes hand in hand with motion. So the more the water molecules are in motion, the hotter it is. And then just above microwaves, little bit shorter wavelength, shorter wavelength, higher frequency is infrared. A lot of people say this wrong. They say infrared. It's infrared, not infrared, infrared. And infrared wavelengths are how heat is transferred, because infrared is that thermal energy. A lot of times, if you've seen like heat lamps, they have a red hue to them because they overlap with the visible red light, but they're also infrared. So radiant heat transfers in the thermal energy of infrared waves. And also like remote controls, they use a light that seems invisible to us. That's just because we can't see infrared waves. because it's a little bit longer wavelength than we can see. Now, the last thing, and CD-ROM drives are also, if you know what those are, they're kind of obsolete now. Like DVD drives, that kind of thing. They usually read the disc using infrared. Now, the last little part of infrared is a word you probably recognize. R-E-D, red. That's because just shorter wavelength, higher frequency than infrared is the first color we can see within the visible light spectrum, and that is red. Infrared goes to red. Then you have red, orange, yellow, green, blue, and violet. All the spectrum of visible light, those are the only wavelengths and frequencies that we can see. And by the way, this little symbol is wavelength. So red is the longest wavelength, violet is the shortest wavelength. It's actually called lambda, but it means wavelength. So we've got infrared, just longer than red. Red, orange, yellow, green, blue, violet. What do you think is going to be just above violet? It's one you've also heard of. It's ultraviolet. That's the next one. So again, this is a very, very small portion of what exists that we can see. So we've covered radio waves, we've covered microwaves, we've covered infrared. Then we have the visible light, red, orange, yellow, green, blue, violet, and then ultraviolet. So ultraviolet waves are just shorter wavelength, higher frequency than visible light. And these are the things that we try to protect against in excess on our skin by wearing suntan lotion and not being outside with exposed skin for too long, because overexposure to UV, by the way, UV is the abbreviation for ultraviolet. Overexposure to ultraviolet waves can cause skin damage as mild as sunburn, but as severe as cancer. Skin cancer is caused by ultraviolet waves. Interestingly enough, a little bit of ultraviolet waves is actually very good for you because it promotes vitamin D, vitamin D synthesis within your body, and that's a vital mineral that we need. So UV light, as I just said, is what enables your body to make vitamin D. And vitamin D deficiency, or in other words, when you don't have enough vitamin D, that's what is responsible for a lot of chronic depression. Because it's the cause of the symptom of depression. So if you're vitamin D deficient, you might be depressed. That's why you should go outside. That's why those sunny days just make you happy. There's a chemical reason, because you make vitamin D, which fights against depression. On the flip side, UV waves can kill. However, they don't just kill you. They can kill bacteria by damaging its DNA. So if you've got bacteria on something, if you have something like if you've got a little brother, sister, a dog, or whatever that throws up on something and they might have been sick, wash it off, rinse it off, and then leave it out in the sun, and all of that stuff should die. And there's also there's UV lights or ultraviolet lights that we used to use to sanitize lab safety goggles, because it kills all the bacteria in those as well. All right, so just shorter wavelength than ultraviolet, higher frequency than ultraviolet is a next category called X-rays. And these are what we use to take X-ray images in the doctor's office, like this one. They're also used by dentists to get images as well. They're a higher energy wave, higher frequency, lower wavelength. And the highest energy, highest frequency, shortest wavelength wave is gamma rays. And the way that I remember this is the comic series on the Incredible Hulk. If you've read it or familiar with it, you know that the Hulk was exposed to gamma radiation. And it makes sense that if he was exposed to the highest energy radiation, he would get all crazy and strong and angry and all that stuff. So the other way is to remember this is ironically calling them gamma rays, because grandmas aren't typically the highest energy individuals in your family, although maybe they are for yours. But gamma rays are the highest energy, highest frequency, shortest wavelength. And some things that produce them are radioactive decay and the stuff that goes on in the sun as well. It's very, very high energy wave. So if we have these nuclear reactions, a lot of times they produce gamma rays. Whoops. Interestingly, gamma rays can kill living things. They can kill your cells. However, if you have cancer cells all located in a specific area, and we can target the gamma rays that we expose you to just that area that has the cancer cells, it can actually kill your cancer cells, and it kills some of your living cells as well, because it kills everything. But the idea is with what's known as quote unquote radiation cancer treatment is that you kill all the cancer cells, you kill some of your healthy cells, but your healthy cells, there's enough of them around there to go through mitosis and make more, and eventually your body repairs itself, but the cancer dies. But it's also very dangerous. That's why a lot of times people with radiation treatment get sick as well. And it just, as I just said, nuclear explosions and fission and fusion usually release gamma rays as well. Now we're going to shift gears a little bit and talk about the behavior of light in terms of visible light. Just to review, light has that wave-particle duality. It can behave as a particle and as a wave simultaneously. And when light encounters an object in its path, it has three options. It can be reflected off of the object, it can be absorbed into the object, or it can be transmitted through the object. Reflected off of the object, absorbed into the object, or transmitted through the object. And this is kind of crazy, anything that you can see reflects light, but not all the wavelengths of visible light. See, when you look at an object, you don't actually see the object. All you see is whichever light is reflected off of the object. That's why if you were able to turn all the lights off in the room, including like little computer lights, and like block all the windows, and it was pitch black, like no light in the room, you couldn't see your hand a centimeter in front of your face, because we don't see objects, we see the light reflected off of objects. So how we see them depends on what the light is doing. And in this case, it appears this spoon is bent or folded, and this is due to a phenomenon called refraction. Refraction is a type of transmission. Remember before we said light can be transmitted through an object? Well, the light is transmitted through the glass and the air and the water. I'm assuming this is water. It's transmitted through, but as it's transmitted through, it changes the speed of light, because light travels at different speeds through different mediums. So it travels at a different speed through the air than it does through the water. So because gases and liquids behave differently. And so it appears to like change the image we see, because the light is changing speeds when it's through the liquid before it gets to our eyes versus when it's just in the open air up here. And that phenomenon where light changes speeds as it goes from one medium into another is called refraction. And it makes it appear that the spoon or any object is bent. Refraction is also the thing that's responsible for you seeing a rainbow. Because all of the Roy G. Biv, red, orange, yellow, green, blue, violet colors of visible light, when they overlap each other, we see white light. All of those colors are in the white light. But a little thing called a prism, the little triangle looking thing, can refract the light. And remember we said that light goes at different speeds through different mediums. As it goes through that clear plastic prism or the glass or whatever it is that's acting as a prism, it stretches out those colors that were overlapping in the white light, and we can see them individually as red, orange, yellow, green, blue, and violet, which is a pretty cool phenomenon. Almost looks like magical. And this is another example of that same thing going on with the white light going into a water droplet, which can act as a prism as well. And that's why you only see rainbows right after a rainstorm, because there's water droplets that are refracting the white light from the sun. Whoops. Yeah, so it's basically the same thing as this picture. This kind of was touched on before, but light color depends on the wavelength and frequency. So like the longest wavelength is red, the shortest wavelength is violet. Also the lowest energy is red, highest energy is violet. Lowest frequency is red, highest frequency is violet. And the color depends on the wavelength. But the object color, so you're looking at an object, it doesn't depend on the wavelength of light. It depends on the wavelength of light that's reflected off of the object, because objects absorb other colors. So if I am looking at a green leaf, which would be somewhere in this region, that means that the white light from the sun has all these colors in it, but the reds, the oranges, the yellows, the blues, and the violets, those are all absorbed by the green leaf, and the only color that's reflected is green. And if I look at a red shirt, that means red is reflected, and orange, yellow, green, blue, and violet are absorbed by the red shirt. So what we see depends on which colors are absorbed and which colors are reflected. We only see the reflected colors. So here's a couple of different things about the behavior of light. Filters, like you put on a camera, they can absorb and transmit selectively. So they can allow specific wavelengths to be transmitted through, and then they absorb other ones. And that's how you can kind of doctor up a picture without bringing it into any kind of Photoshop type thing. But pigment is the opposite of color of light. Pigment is, remember, what we see is what's reflected. So in regards to pigment, we're only seeing the reflected light, not the full picture. And you can kind of see this in here. This is what you would see in pigment, like with ink colors in your printer. You have these three colors. When they overlap, you see black when all of them are overlapping. But with light, it's the opposite. You have red, green, and blue, and they overlap. And where they overlap completely, you see white light. So adding the primary colors together with light gives you white, but with pigment, it gives you black, which is just an interesting dynamic. All right, go ahead and close this down, answer the questions that are attached, and move on.